Welcome to Cloud on Air, live webinars from Google Cloud. My name is Sergey Sokolenko. I'm the product manager for Cloud Dataflow, and today we'll be talking about advancing serverless data processing in Cloud Dataflow, introducing distributed shuffle. You can ask questions anytime on the platform. We have Googlers standing by, ready to answer them. Let's get started. I wanted to spend just a few minutes talking about Cloud Dataflow and what it does. We are an industry-leading platform for serverless stream and batch data processing. Customers use us because we provide unified batch and streaming data processing capabilities. And we offer them in a serverless, fully managed way so that customers don't have to worry about managing infrastructure. We have an open source programming model. It's called Apache Beam. And customers also enjoy the ability to use us when they only have maybe a few records per second streams and ranging up to millions of queries per second. When the team went ahead and thought about how to better improve Cloud Dataflow and simplify the data processing challenges that our customers faced, we realized we needed to re-architecture our data processing infrastructure, actually the way that the industry is doing data processing. And to explain why we needed this re-architecture, let me tell you a quick story. How did the industry solve the problem of processing really large data sets? So imagine it's the year 2000 and you have 1 petabyte of data that you want to process. Well, who am I kidding? In the year 2000, a terabyte-sized data set would be considered really large. So what do you do if it's the year 2000 and we have 1 terabyte of data to process? You would probably use a large mainframe or a Unix box. Remember, it's the year 2000. And you would use SAN, or storage area network storage, that was attached to this big mainframe. As time progressed and new technologies became available, for example, MapReduce, you would switch to a cluster of cheap Linux nodes where storage was actually part of the box. And then as things moved to the cloud, you would still use your cheap Linux infrastructure for CPU, but you would switch to network-attached storage. In 2010, Google published the Dremel paper, which introduced a novel concept of processing large volumes of data by using distributed storage and compute clusters. And in 2011, we launched BigQuery, our flagship data warehouse that was based on the Dremel concept. BigQuery had a replicated and distributed storage. It also had a highly available compute cluster. But they also had something that the original Dremel paper didn't mention, and that's the distributed in-memory shuffle tier that connected both storage and compute. So the question becomes, why did BigQuery introduce this distributed shuffle tier? What was it that caused them to care so much about shuffle? Well, let's answer the question first, what is shuffle? Imagine you have a very large data set, and it's a key value based data set, so you have key value pairs. If the data set is reasonably sized or small in size, you can probably group and join this data set by sorting it and doing it in memory, either on this box, that single box that you have, or on disk. Now, if your data set is actually exceeding the capacity of a single processing node, you have to distribute the processing and sorting over multiple processing nodes, and then it becomes tricky. What you want to basically end up having is a sorted set of your data by key, where keys are assigned to particular processing nodes, and all the records related to these keys are co-located on the same physical machine. And in the process of sorting, you're going to be ending in a shuffle operation where records are physically moved from the boxes they don't belong to locations where they belong to, basically sorted by key. And this is what a shuffle process does. Now, BigQuery processes large volumes of data, and it does it in a distributed way. So it made sense for them to optimize the shuffle step, because it's as you can imagine, such a resource-intensive and time-intensive step. In Cloud Dataflow, in my product, we have very similar needs, and our customers have very similar challenges. They want to group and join data, And we're doing it, we're dealing with large data sets, and so we have to deal with it in a distributed way. We in Dataflow, we ask ourselves the question, can we apply similar concepts of a distributed shuffle to our own pipelines? I wanted to walk you through the life of a batch Cloud Dataflow pipeline as you submit it to the Dataflow service. What happens when you actually send this job to our service? On the left-hand side, I have the graph of the Cloud Dataflow, a Cloud Dataflow pipeline. It's what we call a direct acyclical graph with stages and edges connecting these stages as data flows from top to bottom. On the right-hand side, I have a more simplified representation of this graph. We have data sources. We have data transformations. These are the green boxes. They can be either filtering or projections, aggregations. We also have join and group by operations, and we have sinks, data sinks into which we write results. So what happens if you submit this job to the Cloud Dataflow service? Well, first off, we are going to create a cluster of processing nodes. And then we're going to start reading from data sources. And as we read the information or data elements from data sources, we're going to start applying data transformations on them. We're going to be doing the filterings, the projections, the aggregations. Once we hit the joins and the group bys, we're going to initiate a shuffle operation and use persistent disk volumes that are attached to your processing nodes. Now, at the end, we're going to write into our sinks, data sinks, and shut down this processing cluster. In Dataflow, as I said before, we're dealing with large volumes of data, and very similar to BigQuery, we wanted to optimize the interactions between our compute and storage facilities. So we introduced recently a separate distributed in-memory shuffle component in Dataflow and made it completely transparent to users. As a user, you continue writing your pipelines, and you don't think about whether you want to do shuffle in a distributed way or in any other way. You just specify a parameter that you want to use a Dataflow Shuffle component, and we'll take care from there. Let me explain the architecture of our service. Our user code is still running on a compute cluster, and this compute cluster is connected through a very large and fast petabit network to the Dataflow Shuffle component. The Dataflow Shuffle is deployed in multiple GCP regions, taking care of regional availability. In the regions where we don't have Shuffle deployed, you can still do Shuffle operations. You're just going to be using the persistent disk Shuffle operations available today. But in the regions where we are deployed, we have several components which take care of the Shuffle job. First off, we have the AutoZone placement component. This component is responsible for picking the regional zone in which to run your shuffle job. It will pick the zone based on the available capacity and closeness to your data sources and sinks. Now, once the zone is picked, the shuffle proxy will start interacting with the code that is part of your Dataflow pipeline. And as part of this interaction, the shuffle proxy will accept the data set that you want to shuffle, and then either pick the in-memory file system if your data set fits entirely into memory, or it will partially distribute data between the in-memory and the on-disk file system if the data set is too large to fit into memory entirely. This is all transparent to users, our developers. They don't have to decide how much data is going to be shuffled on disk versus how much data is going to be shuffled in memory. We take care of all the processing. One benefit of this approach is that many customers are reporting they're seeing performance improvements from this re-architecture. So if in the past a pipeline that used persistent disk shuffle might have taken you 45, 50 minutes to process a certain data set, and if after some tuning and using SSD persistent disks, you might have reduced this time down to perhaps 20 minutes, with Dataflow Shuffle, the processing time of such a pipeline is now closer to 10 minutes. The results will not apply uniformly to every pipeline in production, but these are approximate performance improvements that we are hearing from a lot of our customers. Another benefit of Dataflow Shuffle is that we are now able to scale to much larger data sets. In the past, with persistent disk-based shuffle, you were able perhaps shuffle maybe a 50 terabyte large data set. And the reason why 50 terabytes was kind of the magic number was because after that volume, the interactions between your processing nodes, the physical reshuffling of data elements, the coordination between the workers was just too much. With the migration to the Dataflow Shuffle service, you're now able to shuffle much larger data sets. Customers are reporting that they are routinely shuffling 100 terabytes and larger, and the ceiling gets larger and larger with every monthly release of the service. So at this point, I wanted to show you a demo in which I will quickly join two data sets. They're pretty large data sets. In total, they constitute 100 terabytes worth of data. My pipeline is relatively simple. I have two inputs. They are GCS buckets. And each of these buckets, it's actually a single bucket. It contains 50,000 files, 1 gigabyte in size each. And I'm going to explain what the contents of these files is very shortly. So these inputs are being joined in my pipeline, and I write the outputs, which is a join result set of a join, again into GCS buckets. On the right-hand side, you see the code of my pipeline. I use Scala to develop this pipeline, and I also relied on a package developed by one of our customers, Spotify. This package is called Shio. Makes it really easy to write pipelines. I'll quickly explain what happens in this script. If you focus on the main function, I'm defining my left and right inputs. That's my input 1 and input 2. I'm then doing a left outer join of one of the inputs with the other input. And I'm saving the results of this left outer join into a collection of files. Each of the files in my input buckets has 3 columns. Remember, each file is 1 gigabyte large, and I have 50,000 files, a gigabyte in size. So each of these files has 3 columns. The first column represents the key by which I will be joining my data sets. The second column is a sequential number that just iterates through the records located in my input file. And then the third column is the payload. And if I had a production pipeline, I would perhaps have a serialized representation of a business object here, perhaps a sales transaction, or a user clicking on a web page, anything that makes sense to your business. So with this, let me switch to demo mode and show you how easy it is to initiate a Dataflow job that runs and uses Dataflow Shuffle to shuffle a really large data set. In Shell, I've done some prep work, and I've already uploaded all the files in my input buckets. I wanted to show you the command I'll be using to initiate the Dataflow job. This command is using the Scala build tool to run this particular class file, the demo.join, and I'm specifying a few parameters here. First off, I'm going to tell the project in which I want to run this job. I also specify to the Scala build tool that I want to use my Dataflow runner, meaning I want the job to be executed in the Dataflow service. I'm specifying my inputs, and the inputs is actually a shell variable which will result in a filter, kind of in a pattern that specifies about 50 terabytes worth of files. And lastly, I have a command that specifies my my shuffle operation. So if you wanted to know how to launch a shuffle job, what you need to know is just specify an experiments flag, and the flag says shuffle mode equals service. That's all you need to do to run a shuffle job. And incidentally, I also started the job just by playing around with the parameters. It's all good. In a few seconds, you'll see the results of this job submission. Hopefully, it will be a success. It usually takes between 50 to 30 seconds just to send the files back to the service. Before the demo, I've done some similar runs of 100 terabytes in size. So let me show you the results of the jobs that I ran just before the demo. Here's the collection of the Dataflow jobs that I ran previously. Let me pick one, and by the way, already my job is now being run by the service, but it's obviously not finished. So let me still explore one of the previous jobs. It has been successfully executed. Everything is green here. You'll recognize the pipeline graph. It takes 2 inputs and produces an output. Now, just to show you how many data elements this pipeline crunches through, I have 50 billion rows, which will be joined from each side of the join. So both the right and the left side of the join will have 50 billion rows of 50 terabytes in size. The actual join operation happens in what we call a co-group by key. This particular join will create 100 billion groups of the same key. And then the result of my join will be persisted in a GCS bucket. It will actually be a collection, a large collection, probably tens of thousands of files. And it will be almost half a petabyte in size. 2.5 trillion records and half a petabyte of data. So this entire join took me only 7 hours to run, or 7.5 hours to run the day before. And during this execution, I was able to rely on Dataflow's distributed processing capabilities by using 1,000 workers to run my joining, my reading from sources, my joining, and my outputting to destinations. Here's a pipeline graph of the worker history that shows how many workers were used during the execution of this job. After a quick spike to 1,000 workers, Dataflow maintained the number of workers at 1,000. The 1,000 here is a kind of a magic number related to my project. My quota is limited to 1,000 workers, and so this is why Dataflow didn't go above. So for about 7 to 8 hours, 1,000 workers were crunching through these petabytes of data and produced 2.5 trillion output records. Similar to this 100 terabyte run, I also did several similar runs, but just different in size. And I've plotted the graph that represents the duration of these runs in relation to the size of the joins. So my 100 terabyte run is all the way up there in the upper right corner. And I also have 2 additional runs which differ from my 100 terabyte run in size, and I always step down like by 5x reduction in size. So the 20 terabyte run ran 20 terabyte join ran for about 100 minutes, and the 4 terabyte run ran for probably less than 20 minutes. As you can see, Dataflow is able to scale the execution time of my joins pretty linearly depending on the dataset size, which is a great quality of this particular Shuffle implementation. Usually Shuffle starts getting slower and slower and becomes nonlinear when you increase the data size. The other good quality of Dataflow Shuffle is that the resources used for the shuffling of this data set also scaled linearly. You don't see it in the graph here, but if you kind of reproduce the results in your own tests, you would see that the shuffle resources also scaled linearly. So far we talked about batch pipelines and how we do shuffles in batch jobs. Dataflow provides a unified batch and streaming processing environment. And you might ask yourself, well, does this apply to streaming pipeline as well? Do streaming pipelines also need to be able to do shuffle? The answer is yes. Just like in batch, streaming pipelines can also do groupings and joins. You can group and join streams, or you can group and join streams and static snapshots. And this leads to a need to have a distributed streaming shuffle. Very similar arguments apply here as we just discussed in the batch case. In streaming, there is also another consideration which is very important. and that's the state of your window, time window storage. Now I'm going to explain what time windows are and why we need to store data elements related to these time windows. But just suffice to say to know that in streaming, customers typically want to aggregate data elements based on some time dimension, some business time dimension, and we need to accumulate the data elements related to individual time windows in this time dimension until we can actually process them. Let's take a minute to review the life of a streaming pipeline, similarly to how we looked at the life of a batch pipeline. I have a pipeline that reads from PubSub, does a windowing operation, basically windows my input stream by some business time dimension, then does a grouping of data elements, and runs a aggregation operation, a count in this case. It basically counts the number of elements in a group and stores the results in BigQuery. So let's focus on the group by. One thing to remember is in a streaming pipeline, once you submit the job to the Dataflow service, we will divide the job, the streaming job, into 3 phases. Everything before the group by, everything after the group by, and then we'll have the group by operation, which will be implemented as a streaming shuffle. Dataflow deals with very large volumes of data, and the way we deal with these huge volumes of data is by parallelizing work and doing the processing on many, many workers. The way we parallelize work is by dividing our input data sets, kind of sharding the data inputs by key, dividing them by key, and then assigning key ranges to individual workers. So these key ranges become the basic unit of scaling for us, and we only assign and redistribute work between processing nodes by assigning key ranges, and these key ranges become owned by a particular data processing worker. You might ask, where do we take the keys? If your streaming pipeline has a group by key operation, we'll take the key that you specified during the group by key. If you don't have a group by key, we'll actually auto-generate keys and then partition them into key ranges. So let's take a look what happens when you start your streaming job. First off, we'll create a processing cluster of streaming workers. We'll assign the keys to each individual worker. As you see here, the keys of the before shuffle operation and the keys of the after shuffle operation are being assigned to different workers, and some workers might get more work than others. We're going to store the keys and the data elements, the records associated with these keys, on persistent disk. This is how we currently do streaming shuffle. All of the information, very similar to current implementation of batch shuffle before the shuffle service, we are using persistent disk volumes in both cases. And when we have to scale our streaming pipeline, when, for example, we start with 5 processing workers, but realize that our data volume justifies the increase of this cluster to perhaps 10 processing workers, what we're going to do is we're going to start shuffling the disks that store the key ranges that contain the data records. So the entire data disk, the entire PD disk, will be reassigned from one worker to another. And our streaming autoscaling implementation works very well for many cases, but as you can imagine, there is a lot of shuffling of disks going on, and it might not be the fastest way to reassign work between processing workers. Another thing to remember is that the number of disks used in a streaming pipeline, in a current implementation of shuffle in a streaming pipeline, so that number of disks is fixed, and it's determined at the beginning of the pipeline. We typically pick a very reasonable number at the beginning, but then we never change the number of disks for the duration of the streaming pipeline. The only way for us to give more disks to a particular worker is basically by taking an existing disk from another worker. So we just covered how we do group buys and shuffle in streaming. Let's also look at the windowing operation, because it's quite central to the concept of a streaming pipeline. To understand what happens during windowing, let's quickly review what a data stream represents. Typically, customers have two important time dimensions in their data streams. The first important time dimension is the business time of the transaction. We call it the event time. It typically represents some business time stamp. If you have a sales application, when was the sale done? Was it 8 a.m., 9 a.m., some other time? If you have a marketing application, when did the customer interacted with your website? So it's the click time. The other interesting dimension in data processing is the processing time. So this is the time when your data element actually arrives at your processing pipeline. And interestingly, event time and processing time will always differ for pretty much every data element in your stream. And here's why. I have an example of three business transactions that all happened at the same business time. So the sale happened at 8 a.m. My green and my blue and my yellow data element, they all happened at the same time. Now, they actually arrived at different time points in my streaming pipeline. You might ask yourself, why? For example, if the sale happened on a mobile device, that mobile device might have had different bandwidth capabilities. And so as the record was traveling through the networking infrastructure, it took its time and got delayed by almost an hour. Perhaps another customer, the customer who submitted the yellow transaction, was on a plane at that time. And so there was no connectivity, and the sale transaction actually didn't get into a network and into your streaming pipeline up until 3 hours later after it actually happened. So this is why event time and processing time differs. But users actually don't want to deal with processing time. This is not what their business represents. They want to be able to deal with event time. They want to be able to take the input stream, and they would like to be able to divide it into nice windows based on the event time, and then run aggregation operations based on time windows defined on event time. So now that we understand how windowing works, let's kind of conclude and explain how we store these data elements until we can actually do anything on them. Because there's a difference between event time and processing time, we're going to have to cache and store temporarily data elements related to time windows. And we are storing them again on persistent disk, just similar to how we store shuffle data. So the persistent disk volumes have two functions here. They will store your shuffle data, and they will store temporarily the time window data up until the time when we see that no other records related to a time window arrive, and we can trigger our processing on these time windows. The Dataflow Streaming Engine is our implementation of Dataflow Shuffle, but in streaming pipelines. Very similarly to batch use cases, we've asked ourselves, can we improve the processing of Shuffle in streaming cases, and can we improve the state storage, the Windows state storage for streaming? The streaming engine moves the processing of state as well as of Shuffle from the processing workers all the way to our backend service. In the process, users get three benefits. First off, they gain smoother autoscaling. We don't have to move around persistent disks anymore. The other benefit is we can now do much better maintenance of our operations. We don't have to shut down user pipelines. We can maintain our backend infrastructure without impacting customers. And lastly, the user code that still runs on the processing nodes, we are not moving that one. So your user pipeline still runs on a cluster of processing nodes. Your code gets more resources because the operations that used to run, the system operations that used to run on the same processing node have been moved to a backend service, and now suddenly your user code gets more memory and more CPU. Let me give you an example of how autoscaling was improved with the streaming engine. I have a stream of data that I collected over a period of 1 hour, and that stream ranged from 1 to 10 million bytes per second. And I have two distinct spikes, increases in this data stream somewhere closer to the first third of the time period, and then at the end of the time period. When I launched a streaming pipeline without using the streaming engine, I got the following graph of the number of workers that Dataflow service decided to use to process my data. As you would expect, the number of workers initially was quite low. I think it was about 3. But then as the data increased, and as Dataflow service realized that the backlog was growing and we could have used more resources, Dataflow has increased the number of workers all the way to 15 and kept it at that number until the intensity of my data stream declined and we didn't need that many resources anymore. All the way up until the end of the pipeline, where the end of the hour, when the stream rate again increased and we needed more resources. Now compare this graph with the graph with of a streaming pipeline with the streaming engine. The first thing you'll mention or see will be that the number of streaming workers that the Dataflow service will launch at the first spike is going to be smaller than in the previous graph. And I'm actually going to overlay the two graphs so that you see it a little bit better. So Dataflow didn't need as many workers to process your data, because now your system operations such as Shuffle and state storage are running on the backend service. Your user code gets more resources. It has a better throughput rate. The other thing that you will see from this graph is that we are now able to much quicker downsize the number of workers used in a streaming pipeline. We didn't need to wait all the way until we saw the reduction in the data stream. So just to summarize, let me wrap up and transition to and try to answer a few questions that some of you submitted online. The Dataflow team has learned that using a distributed shuffle was really the key component, a really architectural decision for an effective separation of state storage and compute processing. We did this in the batch pipelines. We offered this capability in streaming pipelines. In batch, we are offering Dataflow Shuffle, and it allows your batch pipelines to run faster and scale to larger data sets. In the streaming case, we have the streaming engine, which also leads to improvements in autoscaling and also improvements in separability. These two features are available in 2 GCP regions, in US Central 1 and Europe West 1. Dataflow Shuffle is now in general availability, and the streaming engine is in beta. If you would like to try both of these features or Dataflow in general, please go to cloud.google.com/Dataflow and you'll get all the information you desire. So with this, stay tuned for the Q&A. We'll be back in just a minute after reviewing the questions that were submitted. I would be happy to answer the questions you have. Welcome back. So we did get quite a few questions here, so let's go through them. The first one was, how do I start using the Dataflow Shuffle? If you remember from my demo, I used the parameter that said experiments equals shuffle mode equals service. That's all you need to do to start using the Dataflow Shuffle feature. Incidentally, this is exactly the same way you would specify, with just slightly different parameter name, how would you specify the use of the streaming engine. In streaming engine's case, you would say experiments equal streaming engine equals a particular value. If you would like to know the exact wording of these parameters, just go to the link I shared in the previous slide, cloud.google.com/Dataflow. Go to our docs, and you'll see the parameters there right there. You don't have to change your code. You only have to change or specify a parameter in the submission of the pipeline. The second question is about APIs. Are there any special APIs required to use Shuffle and Streaming Engine? No special APIs are required. You're still thinking in terms of a direct acyclical graph. You write your Dataflow pipelines using either the Python or Java SDK, using the same commands, same transforms that you're used to. Remember, Shuffle and Streaming Engine will be used anytime, and when you decide to use these two components, anytime you use a co-group by key or a group by key. These are the two operations which use Shuffle and Streaming Engine. The third question is about the size, the maximum size of data sets that a Dataflow Shuffle operation can support. 100 terabytes is not the maximum. We've seen customers doing much more than 100 terabytes. As I mentioned before, the ceiling is actually being increased every month, every quarter as we do improvements on the service. Hopefully, by this time next year, I'll be able to add a digit to this number. Another question talks about whether you can use the streaming engine without using Dataflow. So today, the streaming engine and Dataflow service are kind of part of a larger offering. It's currently not possible to use the streaming engine without Dataflow, but it's an interesting consideration. Is the streaming engine free? Do you have to pay for the streaming engine? The streaming engine does generate billable units. Actually, in the Shuffle case and the streaming engine case, the unit of billing and the unit of usage is the amount of bytes you process and run through these services. So they scale very, very linearly with the data sets that you're trying to process. The feature is not free, but it's very reasonably priced. And you can get the pricing information by going to the Dataflow page, cloudgoogle.com/dataflow/pricing. Another question talks about stateful processing with the streaming engine. Can you do stateful processing with the streaming engine? So this is something that I didn't have time to touch upon in the presentation, in the webinar. But Dataflow does have a state API, and the state API will actually work with the streaming engine, where the state will now be stored not on the persistent disks of your workers, but on the back end of our service. So yes, you can do stateful processing. There's a state API for streaming pipelines. And the last question talks about joining streaming data. Specifically, can you join streaming data with master data? So a use case like that would be you have a stream of sales transactions, and you have like a lookup table that converts from a string value to a ID value that you will then use perhaps for storing in a data warehouse. The answer is it's pretty easy to accomplish such a join. In our terminology, I would recommend doing a side input. Side inputs allow you to define lookup tables, so lookup data sets. And as long as they fit into memory of a single worker, maybe a gigabyte or several gigabytes, you do have the leverage of being able to define different machine sizes. So as long as your data set is reasonably large, not measured at terabytes, perhaps gigabytes, you can do a very, very fast in-memory join of streaming data with master data. Now, if your data set is large, you should use the streaming shuffle that is enabled by you specifying the co-group by key operation in your pipeline. And with this, we're good for today. Thank you very much for joining this webinar. I enjoyed sharing more about Cloud Dataflow with you. Stay tuned for the next webinar, Unlocking Data Analytics and Machine Learning with BigQuery ML.